From the dark, you have been told a comforting story that comets are leftovers, dirty snowballs drifting through the solar system, frozen relics from a time before planets existed, ancient debris that occasionally wanders too close to the sun, grows a glowing tail, and then disappears back into darkness. A harmless story, a simple story. And like many simple stories about the universe, it turns out to be wrong. Because one particular comet has forced astronomers to confront something unsettling. Not because of what it is, but because of where it came from. Far beyond the planets, far beyond Pluto, far beyond the vast frozen shell of the Kuiper Belt, beyond even the distant realm known as the Oort Cloud, a place so remote that sunlight itself becomes little more than a bright star, a place where distances stop feeling real, a place that should have remained forever hidden. Yet somehow, something emerged from that darkness. Its name is Comet C 2023 A3, better known as ATLAS. And when the most powerful space telescope ever built turned its golden mirrors toward this visitor, it began revealing clues that may trace the comet's origins farther back in space and time than anyone expected. The telescope responsible is the James Webb Space Telescope, a machine so sensitive that it can detect heat from objects billions of kilometers away, a machine designed primarily to study the first galaxies. Yet now it finds itself investigating something much closer, a wandering fragment of ice and dust, a cosmic refugee, a messenger carrying information from one of the most inaccessible regions of our solar system, and perhaps beyond. The discovery did not arrive with explosions or headlines declaring the end of the world. Science almost never works that way. Instead, it arrived quietly. A few unusual measurements, a handful of spectral signatures, tiny fingerprints hidden within reflected sunlight. The sort of details that seem insignificant until they suddenly reshape an entire field of study. Because when astronomers began analyzing ATLAS, they realized they were looking at material that had remained almost completely untouched since the birth of the solar system. Material older than Earth, older than the moon, older than every mountain, ocean, forest, and civilization that has ever existed. A time capsule preserved for 4.6 billion years. Imagine finding a sealed bottle drifting in an ocean, not a bottle from a decade ago, not a bottle from a century ago, a bottle from the day the ocean itself was created. That is what astronomers believe they are seeing. The solar system is often imagined as a stable place, 8 planets orbiting the sun, predictable, orderly, permanent. Reality is very different. The solar system is a graveyard of collisions, a battlefield of shattered worlds, a place where entire planets may have formed and vanished before Earth even existed. The calm arrangement we see today is merely the aftermath, the survivors, and comets are among the few remaining witnesses. They drift through space carrying chemical evidence from an era long before planets settled into their modern positions, long before the solar system became familiar, long before humanity appeared to ask questions about it. Every comet is therefore a record, a document, a fossil, but not all fossils are equal. Some are damaged, some have been altered, some have passed near the sun so many times that their original chemistry has been erased. Atlas appears different, much different. Evidence suggests it spent most of its existence locked in deep freeze at unimaginable distances, protected from solar radiation, protected from planetary encounters, protected from change itself for billions of years. That alone would make it fascinating. But the James Webb Space Telescope found something even more intriguing. The chemical makeup of the comet appears to preserve clues about conditions present before the planets were fully assembled. Before Earth became Earth, before Mars became Mars, before Jupiter became the giant monster dominating the solar system. To understand why this matters, you first need to understand the scale of the darkness from which comets emerge. Earth sits approximately 150 million kilometers from the sun. That distance is called 1 astronomical unit, 1 AU. Pluto averages roughly 39 AU, already a staggering separation. If Earth were 1 meter from the Sun, Pluto would be nearly 40 meters away. But the Oort cloud may extend tens of thousands of AU from the Sun. Some estimates suggest its outer edge could reach 100,000 AU. At those distances, neighboring stars begin to matter. The Sun's gravitational authority weakens. The border between solar system and interstellar space becomes blurred. You are no longer dealing with planetary scales. You are dealing with cosmic scales. And somewhere within that immense frozen wilderness, countless comets wait. Trillions of them. Most will never approach the Sun. Most will never be seen. Most will spend eternity drifting in darkness. Yet occasionally something disturbs one. A passing star, a gravitational ripple, a subtle tug accumulated over millions of years. The comet's orbit changes, its long exile ends, its journey inward begins. That journey can take millions of years, a slow fall toward a star. A fall that eventually transforms invisible ice into one of the brightest objects in the sky. When Atlas began this descent, humanity did not exist. The Roman Empire did not exist. Dinosaurs did not exist. Most complex life on Earth did not exist. The comet was already moving, already falling, already carrying secrets through the void, toward a future encounter with a species that would one day build telescopes, toward a future encounter with James Webb. And that is where our story truly begins, because the moment Webb focused on this ancient traveler, scientists realized they might be looking not merely at a comet, but at a preserved fragment of the solar system's forgotten infancy, a relic from a time when worlds were still under construction, a survivor from the age of creation itself. And the deeper they looked, the stranger the story became. To understand why Comet ATLAS matters, you must travel backward, not millions of years, not hundreds of millions, billions, back to a time before Earth existed, back to a time when there were no oceans, no continents, no moon hanging over the night sky, no Jupiter dominating the outer solar system, no Saturn with its magnificent rings, no planets at all, only chaos, only dust, only a collapsing cloud drifting through a quiet corner of the Milky Way. The story begins inside a giant molecular cloud, an enormous region of gas and dust floating between the stars. These clouds are so vast that they can stretch for hundreds of light years. Yet despite their immense size, they are astonishingly cold. Temperatures can fall below minus 260 degrees Celsius, only a few degrees above absolute zero. The atoms inside move sluggishly. Chemical reactions happen slowly. Time itself seems frozen. For millions of years, perhaps tens of millions, nothing remarkable happens. Nothing. Then something disturbs the balance. Maybe a nearby star explodes. Maybe two clouds collide. Maybe gravity simply gains the upper hand. Whatever the trigger, part of the cloud begins collapsing inward, and once gravity starts winning, it rarely stops. The cloud shrinks, density increases, temperatures rise, matter accelerates toward the center. Imagine a gigantic whirlpool forming in an ocean larger than entire star systems. That is roughly what happens. As material falls inward, it begins spinning faster. The same reason a figure skater spins more rapidly when pulling in their arms. Angular momentum refuses to disappear. The collapsing cloud flattens into a vast rotating disk. At the center, pressure and temperature continue climbing. Millions of degrees, then tens of millions. Eventually, hydrogen atoms begin fusing. A star ignites. The sun is born. But the sun is only part of the story. Surrounding it remains a colossal disk of leftover material, a disk containing enough dust, rock, metal, ice, and gas to create entire worlds. This is the protoplanetary disk, the construction site of the solar system. If you could somehow stand above it, the sight would be terrifying. Violent collisions erupt everywhere. Dust grains slam together. Pebbles become rocks. Rocks become mountains. Mountains become planetary embryos. Nothing forms peacefully. Everything grows through impact, through destruction, through endless collisions. The solar system was not assembled, it was forged. Every planet you know emerged from this inferno. Earth is not a pristine creation. Earth is the surviving product of countless cataclysmic impacts. The same is true for every world orbiting the Sun: Mars, Venus, Mercury. Even the giant planets, each carries scars from those ancient battles. But not everything became a planet. That is where comets enter the story. As the giant worlds formed, gravity transformed the disk into a cosmic pinball machine. Objects were scattered in every direction. Some were swallowed by planets, some were hurled into the sun, others were ejected into deep space, and some became trapped in remote reservoirs far beyond the major planets. Frozen, preserved, forgotten. Think of a construction site after workers leave. Buildings stand completed, roads are finished, machines are gone, but scattered around the edges remain abandoned tools and leftover materials. Comets are those leftovers, not garbage. Evidence, clues, fragments of the original blueprint. For decades, astronomers believed they understood this process reasonably well. Then, observations began revealing something strange. Comets were not all identical. Some contained unexpected compounds. Some possessed surprisingly high levels of carbon monoxide. Others showed unusual ratios of water and organic molecules. Certain chemical fingerprints suggested formation at vastly different distances from the young sun. It became clear that comets were preserving information about multiple environments inside the ancient solar system. Each one was like a witness describing a different neighborhood of a vanished world. And among those witnesses, some appear more pristine than others. This is what makes long-period comets so valuable. Most comets seen regularly originate from the Kuiper Belt. They circle the sun repeatedly. Every pass strips away material. Every close encounter changes them. Their surfaces become altered, weathered, damaged. But long-period comets are different. Many have spent billions of years in deep freeze, far beyond significant solar heating. Far beyond planetary influence, they are closer to originals, closer to untouched samples from the dawn of the solar system. Atlas appears to belong to this rare category, which means it may carry chemistry that has remained preserved since the earliest stages of planetary formation. Think about what that means. The rocks beneath your feet have been recycled countless times. Continents move, mountains erode, volcanoes melt ancient crust. Earth destroys its own history. Most evidence from our planet's birth is gone forever. Even the oldest terrestrial rocks are only fragments of a much larger lost story. Comets offer something different. They offer preservation, a kind of cosmic deep freezer, a place where ancient material can survive nearly unchanged for billions of years. This is why scientists become excited when a new visitor arrives from the outer darkness. They are not merely observing a comet, they are opening an archive. Reading pages written before Earth existed. And this is precisely why the James Webb Space Telescope became involved. Webb was never built specifically for comets. Its primary mission is far grander. The telescope studies the earliest galaxies, the first stars, the origins of cosmic structure itself. It peers billions of years into the past, looking almost to the beginning of time. Yet that same capability makes Webb uniquely suited for studying ancient solar system objects, because the chemistry hidden inside a comet is extraordinarily difficult to measure. Visible light reveals only part of the picture. Many crucial molecules remain invisible to ordinary telescopes. Water, carbon dioxide, carbon monoxide, complex organic compounds. These substances reveal themselves most clearly in infrared wavelengths. And infrared is Webb's specialty. Its golden mirror spans 6.5 meters. Its instruments operate at temperatures so cold they can detect faint heat signatures across enormous distances. Protected behind a sun shield the size of a tennis court, Webb essentially becomes a giant infrared eye floating 1.5 million kilometers from Earth, an eye capable of seeing what previous telescopes often missed. When scientists pointed Webb toward Atlas, they hoped for better measurements. More precise chemistry, improved understanding. What they found instead hinted at something deeper, something older. a glimpse into conditions that existed before the planets settled into their current arrangement. The implications stretch far beyond one comet, because if Atlas truly preserves primordial chemistry from the solar system's infancy, then every molecule inside it becomes a clue about how planets formed, how water spread through the solar system, how organic compounds survived, perhaps even how the ingredients for life reached worlds like Earth. In other words, this is not merely a story about a comet, it is a story about origins. Your origins, the origin of every ocean, every cell, every living thing, and hidden within the frozen heart of Atlas may be evidence from the moment that story first began. The challenge is extracting those secrets, because comets are deceptive. What looks like a simple glowing object in the sky is actually one of the most complex natural laboratories in the solar system. And when sunlight begins waking a comet from its billion-year sleep, the real mystery finally emerges. A comet looks peaceful from Earth, a glowing head, a shimmering tail, a beautiful object drifting silently through the night. But that image is an illusion. In reality, a comet approaching the sun is undergoing a violent transformation. It is waking up, and the process resembles less a gentle thaw and more the controlled destruction of an ancient world. For billions of years, Comet Atlas likely existed in darkness so profound that human language struggles to describe it. Out in the distant reaches of the solar system, sunlight becomes weak and feeble. The sun itself shrinks into a brilliant star. Temperatures plunge to levels capable of freezing substances that would remain gaseous almost anywhere else. Water freezes, carbon dioxide freezes, carbon monoxide freezes, methane freezes. Even many complex organic compounds become locked in place. Time seems to stop. Imagine placing an object inside the coldest freezer ever built, then leaving it untouched, not for years, not for centuries, but for billions of years. That is roughly what happened to Atlas. Layer after layer of primordial material remained preserved beneath its surface, protected from heat, protected from radiation, protected from change. Then gravity altered its destiny. Something disturbed its orbit, perhaps a passing star. Perhaps a subtle galactic tidal force acting over millions of years. Whatever the cause, the comet began falling inward toward the sun. The journey was unimaginably long, a descent measured not in days or decades, but in geological time. And as it moved inward, nothing appeared unusual at first. The comet remained dark, frozen, invisible, but eventually it crossed an invisible threshold, a boundary where sunlight becomes strong enough to awaken ancient ice. And that is when the transformation began. The first thing most people imagine is ice melting. That is not what happens. Comets do something stranger, much stranger. Many of the substances inside them never become liquid at all. Instead, they sublimate. They transition directly from solid to gas. Imagine a block of ice skipping the liquid phase entirely and turning straight into vapor. That process starts deep inside the comet. Tiny pockets of volatile material begin escaping. Pressure builds, cracks form, gas erupts through the surface, jets burst outward. Dust is dragged into space. The sleeping relic suddenly becomes active, violent, unstable. The comet develops what astronomers call a coma, a giant cloud of gas and dust surrounding the nucleus. This cloud can grow to astonishing dimensions, sometimes larger than entire planets. The solid nucleus may only measure a few kilometers across. Yet the surrounding coma can expand tens of thousands or even hundreds of thousands of kilometers into space. The scale is absurd. Imagine a grain of sand surrounded by a cloud the size of a city. That is roughly the proportion involved. And this coma is where many of the secrets become visible, because every escaping molecule carries information about the comet's interior. Every burst of gas is a message from the distant past, a chemical fingerprint, a clue. The challenge is reading it. This is where the James Webb Space Telescope enters the story. Webb's instruments do not simply take photographs, they perform something far more powerful. They dissect light itself. When molecules absorb or emit infrared radiation, they leave characteristic signatures, distinct patterns, distinct fingerprints. By examining those fingerprints, scientists can identify substances present inside the comet. It is similar to listening to an orchestra. Even if dozens of instruments play simultaneously, a trained ear can distinguish violins from trumpets and drums. Webb performs a similar task with light. It separates the cosmic orchestra into individual players, and when it listened to Atlas, it heard voices from the birth of the solar system. One of the most important discoveries involved water. Water is not rare in the universe. In fact, it appears surprisingly common. Yet understanding where Earth's water originated remains one of planetary science's biggest questions. Did water form locally? Did it arrive through asteroid impacts? Did comets deliver significant amounts? Scientists have debated these possibilities for decades. Every comet observed, therefore, becomes part of the investigation. Each carries a unique chemical signature, a unique history. Atlas provided another crucial data point, but water was only part of the story. Webb also examined carbon-bearing compounds. These molecules are especially important because carbon forms the backbone of life on Earth. Every living organism depends on carbon chemistry. Every cell, every plant, every animal, every human being. The atoms inside your body were assembled using chemical pathways that ultimately depend on carbon's remarkable versatility. Finding carbon compounds inside ancient comets is therefore more than a curiosity. It offers a glimpse into the raw ingredients available during planetary formation, the ingredients that may have seeded young worlds, the ingredients that eventually allowed biology to emerge. And the farther scientists looked into Atlas's chemical inventory, the more they realized they were examining material of extraordinary antiquity. Material that may have remained largely unchanged since before the planets assumed their current forms. This is difficult to comprehend. Human civilization measures history in thousands of years. Recorded history covers roughly 5,000 years. Agriculture emerged around 12,000 years ago. The Great Pyramids are about 4,500 years old. The oldest known fossils stretch back billions of years. Yet even those ancient fossils are younger than the chemistry preserved inside some comets. Atlas is effectively carrying molecules from an era before Earth possessed oceans, before the moon existed, before our planet even finished forming. It is a survivor from a world that no longer exists, a world called the Solar Nebula, the original disk from which everything emerged. And every time sunlight heats its surface, tiny fragments of that lost world escape into space. Webb captures those fragments, measures them, catalogs them, translates them into data. The process sounds clinical, but the implications are profound, because every molecule tells a story. Some reveal temperature conditions in the early solar system, others reveal where specific materials formed. Still others reveal how chemical compounds migrated across enormous distances. Taken together, these clues help reconstruct an ancient environment that vanished billions of years ago. It is forensic science on a cosmic scale. A crime scene investigation conducted 4.6 billion years after the event, and Atlas is one of the witnesses, perhaps one of the best witnesses we have ever encountered. Yet the deeper scientists examined its chemistry, the more another question emerged, a troubling question. If this material truly remained preserved since the solar system's birth, then where exactly did it originate? Not merely from the outer solar system, not merely from the Oort Cloud, but from a specific region of the primordial disk itself, a region so distant and so cold that it may preserve conditions unlike anything found near Earth. And the answer could reveal where some of the oldest surviving matter in the entire solar system was born. Every detective needs evidence, not guesses, not theories, evidence. And in astronomy, some of the most powerful evidence comes from something almost invisible: ratios, tiny differences hidden inside atoms and molecules, differences so subtle that they seem meaningless. until they reveal the location of an event that occurred billions of years ago. This is the secret Webb was helping astronomers uncover because comets do not carry maps. They do not carry labels announcing where they formed. No ancient marker survives saying, I was born 35 astronomical units from the sun, or I originated in the outer edge of the solar nebula. Instead, scientists must reconstruct the past using chemistry. The chemistry becomes the map. Imagine walking into an abandoned house. The furniture is gone. The owners vanished decades ago. Yet traces remain. Dust patterns, scratches on the floor, faded paint. A careful investigator can reconstruct the history of the building from those clues. Astronomers do the same thing with comets. The clues are simply measured in molecules rather than footprints. One of the most important tools involves isotopes. Atoms of the same element can contain different numbers of neutrons. Hydrogen, for example, usually contains a single proton, but a heavier version exists called deuterium. Chemically, they behave similarly, yet their relative abundance can preserve information about ancient environments. Think of isotopes as accents in a language. Two people may speak the same words, but their accents reveal where they grew up. Likewise, isotopic ratios can reveal where material formed inside the early solar system. Temperature plays a crucial role. Certain isotopic arrangements become more common in extremely cold environments. Others dominate in warmer regions. By measuring these patterns, scientists can estimate the conditions present when the material originally formed. And this is where things become fascinating, because the outer solar system was not simply colder than the inner solar system, it was radically different. The young sun flooded nearby regions with heat and radiation. Close to the star, volatile compounds struggled to survive. Only metals and rocky materials remained stable. Farther away, conditions changed dramatically. Water ice could persist. Farther still, carbon dioxide could freeze. Beyond that, methane and carbon monoxide became stable solids. The solar system effectively contained multiple chemical zones, different neighborhoods with different rules, different inventories of material, different opportunities for planetary formation. If you could travel through the primordial solar nebula, it would resemble a gigantic layered ecosystem, not of life, of chemistry. Each region producing unique combinations of compounds, each region leaving fingerprints on anything that formed there. Comets preserve those fingerprints, and Webb's observations were helping decode them. The telescope's infrared instruments can identify molecules with extraordinary precision. Every substance absorbs light at specific wavelengths. Water leaves one pattern, carbon dioxide leaves another, carbon monoxide leaves another, methane leaves another. Complex organics create entire forests of spectral features. To an untrained observer, the resulting graphs look meaningless, jagged lines, peaks and valleys, numbers. But to planetary scientists, they are treasure maps, because every peak corresponds to a molecule. Every molecule corresponds to conditions, and conditions correspond to location. The process resembles reconstructing a vanished city from scattered bricks. No single observation provides the answer, but enough observations reveal the structure. Piece by piece, layer by layer, the mystery becomes visible. For Comet ATLAS, the evidence pointed toward formation in an exceptionally cold environment, an environment where volatile compounds could remain frozen from the very beginning. This matters because extremely cold regions preserve chemistry that warmer regions erase. Imagine placing two identical documents in different environments. One sits inside a climate-controlled vault. The other lies exposed to rain, sunlight, and fire. After centuries, one remains readable. The other becomes unreadable. The same principle applies to primordial chemistry. Cold environments act like archives. Warm environments act like shredders. The farther from the sun material formed, the better its chances of preserving ancient chemical information. This is why long-period comets are so valuable. They may contain some of the least altered matter remaining in existence, not merely ancient, original. And here's where the story becomes even stranger, because some of the molecules observed in comets may actually predate the solar system itself. Read that again. Predate the solar system, before the sun existed, before the planets existed, before the solar nebula even formed. Certain molecules appear capable of surviving the collapse of the original molecular cloud, passing through the birth process largely intact. If true, then some atoms and compounds inside Atlas may be older than the solar system itself, older than every planet, older than the sun. Ancient immigrants from an earlier cosmic era, material inherited from interstellar space. This possibility transforms comets from solar system fossils into something even more extraordinary. They become bridges, connections between the birth of our planetary system and the larger galaxy surrounding it, a kind of chemical continuity stretching across billions of years. Think about your own body. The calcium in your bones, the iron in your blood, the oxygen in every breath. These atoms originated in ancient stars, stars that died long before the sun was born. You are already connected to the distant past. Comets simply preserve that connection more clearly. They are less processed, less altered, closer to the source. And Webb's observations suggest Atlas may be carrying some of the clearest evidence yet of those primordial origins. Yet chemistry alone is not enough. Scientists also need dynamics, motion, orbits, trajectories, because understanding where a comet formed requires understanding how it traveled. And that journey is astonishing. The solar system we see today is not the solar system that existed 4.6 billion years ago. The giant planets moved. Gravitational relationships shifted. Entire populations of objects were scattered. Worlds migrated. Chaos ruled. Some models suggest Jupiter acted like a wrecking ball. Others suggest Neptune migrated outward, throwing countless icy bodies into distant space. The consequences were enormous. Objects that formed relatively close to the sun may have been flung into the Oort Cloud. Others may have been ejected entirely. The modern solar system became a rearranged version of its original self, like a city after an earthquake. The buildings remain, but their history becomes harder to reconstruct. Comets help solve that puzzle. They are survivors of the migration era, witnesses to the great reshuffling. And Atlas appears to be one of the most informative witnesses yet encountered, because the farther scientists trace its chemical ancestry, the closer they come to answering a profound question. Not where the comet is now, not even where it spent most of its life, but where exactly it was born. A birthplace hidden in the frozen outskirts of a vanished disk. A birthplace that may reveal what the solar system looked like before the planets became the worlds we know today. And when Webb's measurements were combined with modern models of planetary migration, an extraordinary picture began to emerge. A picture involving giant planets, gravitational violence, and one of the largest acts of cosmic displacement in solar system history. The solar system you know is a lie, not a deliberate lie, not a scientific mistake, just a snapshot, a single frame taken long after the main event ended. When you look at the planets today, everything appears stable. Mercury circles close to the sun, Venus follows, Earth moves along its familiar path, Mars drifts beyond, then come the giants, Jupiter, Saturn, Uranus, Neptune. A neat arrangement, predictable, almost elegant. It feels permanent. But permanence is an illusion, because the early solar system was a place of violence, a place where planets wandered, a place where worlds migrated across enormous distances, a place where gravity transformed order into chaos and then somehow back into order again. And if Comet ATLAS truly preserves evidence from the dawn of the solar system, then it may also preserve evidence from this forgotten era. An era planetary scientists sometimes describe as the solar system's adolescence, a dangerous period when nothing had settled yet. To understand why, imagine building a city. At first, there are only construction sites. Roads are incomplete. Buildings are unfinished. Heavy machinery moves constantly. Everything changes from day to day. Only later does the city stabilize. The early solar system was similar. The planets did not emerge instantly in their current positions. They formed within a disk filled with gas, dust, and countless smaller objects. And that disk exerted forces, subtle at first, powerful over time. The giant planets were especially vulnerable. Jupiter formed rapidly. Its immense gravity allowed it to capture enormous quantities of gas. Eventually, it became the monster we recognize today, a world more than twice as massive as all the other planets combined, a gravitational king ruling the solar system. But even kings can move. As Jupiter interacted with the surrounding disk, its orbit began shifting. Not dramatically at first, just a slow drift, yet over millions of years, small changes accumulate. Saturn was moving as well, so were Uranus and Neptune. And because these planets were massive, every movement altered the gravitational architecture of the entire solar system. Picture four giant ships crossing a frozen lake. The ships themselves move slowly, but the waves beneath the ice spread everywhere. Everything nearby feels the disturbance. The giant planets created similar disturbances through gravity, and those disturbances had consequences, enormous consequences. Modern computer simulations suggest that at some point the giant planets entered a period of instability, a gravitational chain reaction. Orbital resonances amplified, planetary paths shifted, countless smaller objects were scattered in every direction. The event may have lasted millions of years, or perhaps tens of millions. Either way, it fundamentally reshaped the solar system. This period is sometimes associated with what scientists call the Nice model, named after the city in France where key aspects of the theory were developed. According to this picture, the outer planets did not always occupy their current locations. Neptune likely formed much closer to the sun than it is today, then migrated outward. As it moved, its gravity acted like a giant snowplow. Sweeping through populations of icy bodies, some objects were thrown inward, others were thrown outward. Many were lost forever, and some became trapped in distant reservoirs, such as the Oort Cloud. The consequences were staggering. Imagine detonating an explosion inside a library. Books fly in every direction. Some remain nearby. Some land on distant shelves. Some are ejected through the windows. Thousands of years later, investigators trying to reconstruct the original arrangement would face a daunting challenge. That is essentially what planetary scientists confront today. The solar system's original structure was disrupted. The evidence became scattered. Comets like Atlas are among the surviving books, fragments of a library destroyed billions of years ago, and they still contain information about where they once belonged. Jupiter played a particularly important role. Its gravity is so immense that it effectively acts as the solar system's gatekeeper. Objects approaching the giant planet rarely leave unchanged. Some are captured, some collide, some are accelerated, some are expelled entirely. Jupiter has ejected countless objects into interstellar space. In a sense, it functions as a giant gravitational cannon. And during the chaotic early era, that cannon fired repeatedly. Many comets currently residing in the Oort Cloud may owe their existence to Jupiter's gravitational influence. Without Jupiter, they might never have reached those distant regions. Without Jupiter, some might have collided with planets. Others might have remained closer to the sun. Instead, they were launched outward, cast into darkness, stored in deep freeze for billions of years. Atlas may be one of those exiles, a survivor of the Great Scattering, a refugee from the solar system's most violent period. And that possibility changes how scientists interpret Webb's observations. Because the chemistry preserved inside the comet does not merely reveal where it spent billions of years. It may reveal where it formed before being thrown outward. Those are two very different locations. Think of finding an old photograph in an attic. The attic tells you where the photograph was stored. The image itself tells you where it was taken. Comets work the same way. The Oort cloud is the attic, the chemistry is the photograph, and Webb is helping scientists read the picture. What they are seeing suggests that Atlas originated in an environment of extraordinary cold, a region rich in volatile compounds, a region capable of preserving delicate chemical structures. Yet, that birthplace may not correspond exactly to the location where the comet spent most of its existence. Planetary migration likely intervened. The giant planets moved, the comet moved, the entire solar system shifted around it. Tracing that history requires combining chemistry, orbital dynamics, and massive computer simulations. It is one of the most difficult reconstruction problems in astronomy, but it is also one of the most important. Because understanding comet origins means understanding planetary origins. The two stories are inseparable. Every planet formed from the same primordial disk. Every comet emerged from that environment as well. They are siblings, different outcomes of the same process. Earth became a living world. Jupiter became a gas giant monster. Atlas became a frozen archive. Three radically different destinies, one shared birthplace. And the more scientists study objects like Atlas, the more they realize how much of Earth's history may be tied to these ancient wanderers. Because the great planetary upheaval did not merely scatter comets, it may also have delivered essential materials to the young Earth: water, organic compounds, carbon-rich molecules, perhaps even some of the ingredients required for life itself. The same chaos that exiled Atlas into darkness may have helped transform Earth from a barren rock into a living planet. Which means this comet is not merely a witness to the solar system's past. It may be connected to your own existence, to every ocean on Earth, to every forest, to every heartbeat. And that possibility leads directly to one of the most profound questions in planetary science. Did comets help create the conditions necessary for life, or were they simply passengers in a story already unfolding? The answer may be hidden inside the chemical inventory Webb is now helping reveal. And what scientists are finding inside these ancient icy relics is far more complex than anyone once imagined. If you sliced open Comet Atlas and examined its interior, you would not find a pristine crystal. You would not find a perfectly preserved snowball. You would find something stranger, a frozen chemical archive, a chaotic mixture of ice, dust, carbon compounds, minerals, and molecular fragments assembled before Earth was even finished forming. For generations, scientists described comets as dirty snowballs. The phrase became famous because it was simple, easy to understand, easy to visualize, and profoundly incomplete. Because modern observations reveal that comets are chemically rich environments. Some contain dozens of identifiable compounds, others contain even more. Every new mission, every new telescope, every new observation expands the inventory. And the James Webb Space Telescope is revealing that the chemical complexity of these objects may be greater than previously imagined. This matters because chemistry is destiny. Planets are built from chemistry. Atmospheres are built from chemistry. Life itself is chemistry organized into astonishing complexity. If you want to understand how Earth became habitable, you must understand the ingredients available during its formation. And some of the best preserved ingredients are found inside comets. Imagine discovering a sealed pantry from the earliest days of civilization. The food would tell you what people ate. The tools would reveal how they cooked. The storage methods would reveal what resources they valued. In a similar way, the molecular inventory inside a comet reveals what raw materials were available during the solar system's infancy. The findings can be surprising. Water, of course, attracts the most attention for obvious reasons. Every known form of life depends on it. Earth's oceans cover more than 70% of the planet's surface. Your own body is largely water. The search for water elsewhere in the universe often serves as a proxy for the search for habitability. Yet water alone is not enough. A planet can possess vast quantities of water and remain lifeless. The deeper question involves organic chemistry, carbon compounds, nitrogen compounds, molecules capable of participating in increasingly complex reactions, the building blocks from which biology eventually emerges. Comets appear rich in such materials. Scientists have identified methanol, formaldehyde, hydrogen cyanide, various hydrocarbons, and numerous other compounds. Some are relatively simple, others are surprisingly complex. The significance is difficult to overstate because these molecules did not form inside living organisms. They formed naturally, without biology, without cells, without DNA. The universe appears capable of producing remarkable chemical complexity all by itself, long before life enters the picture. That realization has transformed astrobiology. Life no longer appears to require impossibly rare ingredients. Many of the necessary components seem common throughout the cosmos. The challenge is assembling them into something alive, and comets may have served as delivery vehicles. For decades, scientists have debated the extent to which comets contributed material to the young Earth. The debate remains active. No single answer satisfies every observation, yet the possibility remains fascinating. Early Earth endured a period of intense bombardment. Asteroids collided frequently. Comets likely struck as well. Every impact delivered material. Some impacts vaporized water, others deposited it. Some delivered carbon compounds, others altered atmospheric chemistry. The cumulative effect may have been enormous. Imagine millions of deliveries arriving over hundreds of millions of years. Each shipment small, the total transformative. That is roughly the scenario researchers investigate. The young Earth was not isolated, it was connected to a wider ecosystem of impacts and exchanges. Material moved throughout the solar system. Worlds shared resources. The ingredients of life may have traveled vast distances before finding a home. Comet ATLAS offers a glimpse into that ancient inventory. Not because it struck Earth, it never did, but because it preserves the types of materials that existed during that era. Materials available for delivery, materials available for chemistry, materials available for possibility. The James Webb Space Telescope excels at identifying many of these compounds because infrared spectroscopy reveals molecular fingerprints with extraordinary clarity. Every molecule vibrates differently. Every bond absorbs energy differently. The resulting patterns allow scientists to distinguish one substance from another. Webb essentially turns light into a chemical census, and what it sees inside ancient comets helps reconstruct the environment from which the planets emerged. Yet perhaps the most astonishing implication is that some of these molecules may have formed before the sun itself existed. This idea sounds almost impossible at first. How could material inside a solar system comet be older than the solar system? The answer lies within interstellar space. Long before the sun formed, the molecular cloud that gave birth to our system already contained chemistry. Tiny dust grains acted as chemical laboratories. Atoms accumulated on their surfaces. Reactions occurred. Molecules formed. Over immense spans of time, increasingly complex compounds emerged. When the cloud eventually collapsed, some of that chemistry survived. Not all of it, but enough. Fragments passed through the birth process, preserved within icy bodies, locked inside comets. If this interpretation is correct, then ATLAS is not merely preserving the history of the solar system. It is preserving fragments of a pre-solar history, a history extending even farther into the past. Think about what that means. Some molecules inside the comet may have existed before the sun emitted its first light, before Earth existed, before any planet in our system existed. They survived the collapse of a molecular cloud, the birth of a star, the formation of planets, the migration of giant worlds, the scattering of icy bodies, billions of years of cosmic evolution. And now they are being examined by creatures who evolved on a small rocky planet orbiting that same star. The chain of events borders on the absurd, yet it is real, and Webb is helping reveal it. The telescope's observations suggest that ATLAS contains chemical information reaching extraordinarily deep into cosmic history, deeper than ordinary planetary geology, deeper than Earth's oldest rocks, possibly deeper than the solar system itself. This is why astronomers become so excited about what appears to be an ordinary comet. They are not studying a glowing object. They are studying memory, the memory of matter, the memory of chemistry, the memory of creation. Every molecule inside ATLAS survived against overwhelming odds. Every molecule tells part of a story stretching across billions of years. And collectively, those molecules raise an unsettling possibility. If the ingredients necessary for life are widespread, if complex chemistry emerges naturally, if planetary systems routinely distribute those materials across multiple worlds, then Earth may not be unique. The conditions that produced life here may not be extraordinary at all. They may simply be one expression of a much larger cosmic process. This a process that has been unfolding throughout the galaxy for billions of years. And if that is true, then Comet Atlas is not merely telling us about our own origins. It may be telling us something about countless other worlds orbiting distant stars. Worlds the James Webb Space Telescope has studied as well. Worlds where the same chemistry may have taken root. Worlds where the same ingredients may have assembled into something unexpected, something alive. There is something deeply unsettling about age, not human age, cosmic age, because the numbers become so large that ordinary intuition collapses. A century feels long, 1,000 years feels ancient, 10,000 years reaches beyond most recorded history. But comets like Atlas operate on an entirely different scale. They are measured in billions. And when you begin thinking in billions, you are no longer discussing history. You are discussing eternity. The Earth formed roughly 4.54 billion years ago. The Moon emerged shortly afterward from a cataclysmic collision. The oldest surviving rocks on Earth are around 4 billion years old. Life appeared surprisingly early, perhaps within a few 100 million years after the planet cooled enough to support stable oceans. Since then, every chapter of Earth's story unfolded. Continents formed and shattered, oceans opened and closed. Species emerged and vanished. Dinosaurs ruled, dinosaurs died, mammals inherited the planet, human beings appeared, civilizations rose, civilizations fell. All of recorded history occupies only the thinnest sliver of that timeline. If Earth's history were compressed into a single day, human civilization would appear in the final seconds before midnight. Yet Comet Atlas preserves material from before much of that story even began, before the first oceans, before the first cells, before Earth finished becoming Earth. And that changes the way astronomers think about these objects, because most things in the solar system evolve, planets evolve, atmospheres evolve, stars evolve, even galaxies evolve. Everything changes, everything ages, everything is rewritten by time. Comets are unusual because they resist that process, not perfectly. Nothing escapes change forever. But some comets experience far less alteration than planets do. They spend billions of years isolated in darkness, far from sunlight, far from collisions, far from geological activity, preserving information that would otherwise disappear. Imagine possessing a photograph from the construction of an ancient city, not a painting created centuries later, not a written description, an actual photograph. The value would be extraordinary. That is essentially what scientists seek in objects like Atlas. Direct evidence from the solar system's formative years, evidence that has not been heavily modified by later events. The James Webb Space Telescope is particularly valuable because it can examine chemical signatures at levels of precision previously impossible. Earlier telescopes provided important observations. Ground-based observatories contributed immensely. Spacecraft missions transformed our understanding. But Webb brings something different. Sensitivity, the ability to detect faint molecular signals hidden within the comet's coma. Signals carrying information from deep inside the nucleus. Information that may not have seen sunlight for billions of years. Every observation becomes a conversation with the past, and sometimes the past answers unexpected questions. One of the most intriguing discoveries emerging from modern comet science is that these objects appear far more diverse than researchers once believed. There is no single comet recipe, no universal composition. Some contain relatively abundant carbon monoxide, others contain less. Some appear rich in organics, others display different chemical balances. The differences matter because they suggest formation in distinct environments, different temperatures, different regions of the protoplanetary disk, different histories. The solar system was not chemically uniform. It contained neighborhoods. Each neighborhood left its signature on the objects born there. Comets preserve those signatures, and by comparing them, scientists can reconstruct a map of a world that vanished billions of years ago. This is one reason why every newly observed long-period comet generates excitement. Each arrival represents another data point, another witness, another opportunity to test theories about solar system formation. Atlas is especially important because its apparent preservation state suggests access to particularly ancient material potentially less altered than that found in many shorter period comets. The implications reach beyond planetary science. They touch on a broader question, a question that has haunted humanity for centuries. Where did we come from? Not geographically, not culturally, physically, cosmically. Where did the ingredients that became us originate? The answer begins with stars. Heavy elements such as carbon, oxygen, nitrogen, and iron are manufactured inside stellar furnaces. Some stars explode, others shed their outer layers. Either way, enriched material enters interstellar space. Future generations of stars inherit those elements. The cycle repeats. You are therefore connected to ancient stellar deaths. Every atom inside your body carries a history older than Earth. Carl Sagan famously summarized this idea by saying, "We are made of star stuff." The phrase became famous because it is true, but comets add another layer to the story. They preserve evidence of how that star stuff became planetary stuff, how atoms transformed into molecules, how molecules accumulated into worlds, how worlds acquired oceans and atmospheres, how chemistry gradually created environments where life could emerge. Atlas occupies a critical position within that chain, a bridge between interstellar history and planetary history, a bridge between stars and life. And perhaps that is why these icy visitors inspire such fascination, because they seem insignificant at first glance. Tiny objects, fragile objects. Yet they carry information connecting some of the largest questions humanity can ask. Questions about origin, questions about destiny, questions about whether life elsewhere might follow similar pathways. When Webb studies a distant galaxy, it looks billions of years into the past.